All right, so I want to look at lesson 7 with you today, which is mainly focused on compound events and like finding their theoretical probabilities. I just want to review something that I said in the last video. And I want to make a note that when I write this stuff out the way I'm writing it right now, this is not like the proper way that a mathematician would write these things out. It's just a way that I think, 7th graders would understand it more so than if I wrote it like the actual proper way. And so in lesson 6 and in yesterday's video, like two main things that I want you to know is like how to deal with the word or and how to deal with the word and when we're talking about probabilities. And so if you need to know the probability of this or that, right? The probability of like rolling a 2 or a 3 or spinning a spinner and getting a purple or a blue. Well, then you just take the probability of the first thing, the probability of this, whatever that number is if you know it, and you add it to whatever the probability of the other thing is, right? So the word or essentially just means, hey, add the probability. So let's get a bigger number because this is going to be easy. And then the other thing is, what if you need the probability of this and that? So this is different than this or that, right? This and that is much harder. That means, hey, you have to do this thing and you have to do the other thing, and that lowers your probability because you're like, oh man, I gotta flip the coin heads and I gotta pull a green cube and I gotta roll a 3 or whatever. Like that's really hard, and so you need this number to be smaller to represent that smaller probability, and you get that through multiplication. So this is going to be, if you need the probability of this and that, then you take the probability of this, the first thing, and you multiply it by the probability of that other thing. And that is, that's what we call compound probability. Doing this, when you wind up multiplying probabilities so that you get the probability of two things both happening, or it could be 3 things or 4 things or 5 things, whatever. It's called compound probability. And we use those when we're dealing with compound events. Compound events just means events with like chance experiments with multiple stages. And so it looks like we're going to be talking about that weird family that rolls the 4-sided die to see if they're going to play a board game or a card game again. So let's look at what they want us to do here. It says, recall a previous example where a family decides to play a game each night, and they all agree to use a 4-sided die in the shape of blah, blah, blah. Okay. The tree diagram mapping the possible overall outcomes over 2 consecutive nights was as follows. Okay, so this is the same tree diagram we were looking at in lesson 6, where they could go board game, board game, board game, card game, card game, board game, card game, card game. All right, and so let's see what they want us to do now. It looks like they've expanded the tree here to also include Wednesday. So now this is a 3-stage compound chance experiment instead of just 2-stage, because we're going over 3 days here. But how would the diagram change if you were interested in mapping the possible overall outcomes over 3 consecutive nights? To accommodate this additional 3rd stage, you would take steps similar to what you did before. You would attach all possibilities for the 3rd stage, in this case Wednesday, to each branch of the previous stage. So now they could go board game, board game, board game, board game, board game, card game, board game, card game, board game, board game, card game, card game, etc. I guess I don't really need to say them all. But see, what they've done is after the 2nd stage, BC, BC, they've added a BC branch onto each one of those. And so now there's a lot more possible outcomes for this 3-stage experiment, because they've essentially doubled, right? For however many we had before, now we have 2 more. And for this outcome, now we have 2 more. And for this outcome, now we have 2 more. And so where there used to be 4 outcomes before, now we have 8. And if we did another day, we would wind up with 16. And if we did another day, we would wind up with 32, etc. Okay, so question 1, if BBB represents 3 straight nights of board games, what does CBB represent? Well, I don't feel the need to write that down. I think you get the idea that that means they played card game on Monday, then board game on Tuesday, board game on Wednesday. Number 2, list all outcomes where exactly 2 board games were played over the 3 days. Okay, so I go back and I look at all my possible outcomes and I find the ones where exactly 2 board games were played. So BBB doesn't work because they played 3 board games. But here's one, here's one, here's one. That's it. It looks like I only see 3 where they played board games twice. Okay, so it wants me to list those outcomes. So that's BBC, BCB, and CBB. And now it says there are 8 possible outcomes representing the 3 nights. Are the 8 outcomes representing the 3 nights equally likely? Why or why not? Well, it doesn't really say on this tree diagram here, but we know that the way this family plays it is card games are only a 0.25 probability because they only play a card game if it comes up a 1 on the die, and the board games have a 0.75 probability because they play a board game if it comes up 2, 3, or 4 on the die. And so that's going to mess up these outcomes here. Like the most likely outcome is board game, board game, board game, right? Because that each board game roll has a 3 out of 4 chance. So this is the most likely outcome. The least likely outcome is card game, card game, card game, right? Because it'd be pretty hard for them to roll 1, 1, 1. And so no, they don't. All the outcomes are not equally likely. I'm surprised in question 2 they didn't ask us to write this probability. They should have asked, what is the probability that they will play exactly 2 board games in a given night? Oh, well, you know what? I guess we'd have to calculate a lot of stuff to figure that out. Okay, I guess I see why they didn't ask us that. All right, let's move on. So we're still looking at this family with the board games and the card games, and I don't know if you can see it in the video, but underneath each B they have written 0.07, not 0.075. I don't want to make that mistake as last time. 0.75, and underneath every C they have written 0.25 to represent that the board game always has a 75% chance of coming up and the card game always has a 25% chance. And so I could read this whole thing, but I'll just tell you what the point of this is. Now we can multiply all of the probabilities in each branch to get the overall probability of a specific outcome. So for example, the outcome of playing a board game, board game, board game, like all 3 nights, is 0.75 for the first night, times 0.75 for the second night, times 0.75 for the third night, which they've done here, if you can read it. And when you multiply those 3 numbers, you get 0.421875. So in other words, there's about a 42% chance that they're going to wind up playing a board game 3 nights in a row. Well, I already know what the exercise they want us to do here is calculate all of the probabilities for all the various outcomes. So let's calculate the probability of the outcome board game, card game. So that means it's going to be 0.75 for the first night of board games, times 0.75 for the second night of board games, times 0.25 for that night of card games. So we multiply that together, 0.75 times 0.75 times 0.25. Oops, now I gotta start all over. 0.75 times 0.75 times 0.25 equals, so that number was way too small, so I must have messed up in there. Let me make sure I get it right this time. 0.75 times 0.75 times 0.25. There we go. So 0.140265. And one thing you might notice is that this number is a third of that number, right? 0.14. If you take 14 and multiply by 3, you get 42, the first digits appear. And that's because we multiplied all the same numbers, 0.75, 0.75, 0.75, 0.75, except for the last numbers, I did a 0.25 instead of 0.75, and 0.25 is 1/3 of 0.75. So the answer came out 1/3 as big as this one. What's cool is because of the commutative property of multiplication, I know that any combination of two B's and a C is going to come out to that same answer, right? I'm just going to wind up doing 0.75 times 0.75 times 0.25, maybe in a different order, but the numbers are still the same. The product still comes out the same. So BCB, that has to also be 0.140625. And CBB, that has to also be 0.140625. So we can get a couple of those done kind of quick. And then I can use the same idea by kind of cheating off the answer that the book has given me right here. I don't know if you can read this, but in order to calculate CBC, the probability of CBC, I should say, they've done 0.25 times 0.75 times 0.25, and they got 0.046875, or a little bit less than a 5% chance of playing 2 card games and a board game. And now any combination that has 2 C's and a B is going to have that same answer just because you're multiplying the same numbers just in a different order. So CCB, the probability of that will be 0.046875. And BCC, the probability of that will be 0.046875. Now the only one we have left to do is calculating the probability of card game, card game, card game. And that's going to be 0.25 times 0.25 times 0.25. If we were doing this as a fraction, it'd be 1/4 times 1/4 times 1/4, which would be 1/64. That's going to be less than 2%. Let's see. 0.25 times 0.25 times 0.25. 0.015625. So about 1.5% chance. 0.015625. Right? That's a super small chance. If you move that decimal point over 2 spots to turn this into a percent, you get 1.56 blah, 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 whatever. There's only about a 1.5% chance that they will wind up playing a card game 3 nights in a row. So that's super rare that should ever happen, right? So let's see here. We already finished the question down on this side of the page. That's why I'm moving up here. It says, what is the probability that there will be exactly 2 nights of board games over the 3 nights? So we have to look at all of the outcomes that produce 2 nights of board games. So we go back to our sample space and we look for all the different outcomes with 2 nights of board games. We have this one, and this one. The same 3 that we listed on a question on the previous page. And where I said, oh, I'm surprised they didn't ask us to calculate that probability. Well, now they want us to, now that we have all the correct information. So what they want is the probability of either B, B, C, or B, C, B, or C, B, B. Those are the 3 outcomes that produce 2 nights of board games each. And so if we want the probability of this, or this, or this, we just add up their individual probabilities. So that means we're going to do the probability of B, B, C plus the probability of B, C, B. Look at all these letters we're using. This is crazy, right? Like, I hope this isn't too bad for anybody. If I was teaching this in class, I could like look at your guys' faces and see whether or not you're like totally confused or lost because we were just doing all this math, which is nothing but like a bunch of letters. But I don't know, I can't see your faces, so I don't know if you're like, yeah, I got it, Mr. Thomas, just add them up, no big deal. Or if you're like, what? I hope you're getting it okay. So the probability of BBC, we go back over here, we figured that out as 0.140625. And then actually, because they have the same number of board game and card games in these outcomes, remember their probabilities all turned out to be the same. They're all 0.140625. So we're going to do 0.140625 plus 0.140625 plus 0.140625. And we get, I can just do 0.14065 times 3. 0.14065 times 3 equals... Oh, I should have known it was going to come up to that number because I made that point about this number being 3 times bigger a moment ago. And so I should have known that when I multiplied by 3, I would get that number. And so if you don't think too much about the order of, like, whether they play 2 board games, then a card game, or board game, card game, board game, whatever, they have the same probability of winding up playing 2 board games and 1 card game as they do just playing all board games. And combined, those make up like 84% of the whole thing. You know, so that's a really good chance that they're going to play a lot of board games because of the way they have it set up, right? The 3 numbers out of 4 get to a board game instead of, and then only 1 number gets you card game. All right, I think that's going to be it for this today. If you're watching this on Friday morning, which I think you should be, then you should come and play a Kahoot with me in office hours. It's probability Kahoot games, 10 to 11 today. All right, see ya.